Hi there, this is Tiffany Fugate, and today we are going to derive the formula for the sum of a finite geometric sequence when the domain is the set of natural numbers. So, let's first look at the terms of the sequence. So, the first term, let's see if I can clear that up a little bit. Okay, the first term in this sequence, a sub 1, is going to be some a value times a common ratio. When looking at geometric sequences, you really have to pay attention to where is this sequence starting. Sometimes you will start with a domain of the natural numbers, which includes with this first term the common ratio. Sometimes you'll start with a domain of the non-negative integers, which means that you would back it up to a sub 0 equaling a. So you kind of have to really pay attention to how many terms you're summing, because you may or may not be adding in an extra term. So you really have to pay close attention there. Alright, so on with this. A sub 2 is a times r squared. A sub 3, a times r cubed, because the subscript should line up with the exponent. So as we go on, a sub n will be a times r to the nth power. Alright, so now we want to add the terms of the sequence together. Okay, so we're going to look at the sum as k goes from 1 to n. Alright, of any arbitrary geometric sequence. So a times r to the k power. So the k is going to be our index here for the sum. This is telling us that the exponents on r are going to be moving consecutively from the integers between 1 and n. So 1, 2, 3, 4, so on and so on, all the way until we get to whatever n is, which is our stopping point. Okay? Alright, so this is going to look like, and some people use this notation. I don't prefer this notation because it's not as descriptive as the summation notation over here on the left. But what we're going to do is we're going to take all of these terms and add them up. But we're going to use the notation over here on the left. On the right. So that's going to be AR plus AR squared plus AR cubed plus dot 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 plus AR to the nth power. And I'm going to call this equation 1. Alright? Now, in order to find the closed form of the sum of a finite geometric sequence, I'm going to take equation 1 and multiply it by a factor of r, and I'm going to call that equation 2. So just using the distributive property here, I'm just going to go through and raise the power of r on each term by 1. I'm going to increase each power of r by 1. So this will be ar squared plus ar cubed plus AR to the 4th plus dot 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 plus AR to the nth plus AR to the n plus 1. Okay? Alright, almost there. Alright, so now, in order to find the closed form, what we want to do is we want to take equation 2 and subtract from that equation 1. And what's going to happen when we do that is several of these terms are going to be reduced to 0. Okay? So equation 2, first of all, on the left-hand side, this summation has a coefficient of r, this one has a coefficient of 1, so we're going to be looking at r minus 1 times the sum, k going from 1 to n of a r to the k. equals r minus 1 of s sub n, which indicates the sum, which is our less descriptive notation. Remember, we're going to prefer this one, but some of you may not be comfortable with this, so I'm using an alternate. And now let's look and see what terms are going to be left. Okay? Remember, we're doing equation 2 minus equation 1. So this term here, a times r to the n plus 1. Now look, we've got a times r to the n minus a times r to the n. And then if you keep backtracking, you would have a times r to the n minus 1 minus a times r to the n minus 1. Your a times r to the 4th is going to reduce to 0. A times r cubed is going to reduce to 0. The r squared is going to reduce to 0. So you're going to be left with minus a times r. Okay? So look how nicely that simplifies down. So now the only thing left to do is to divide everything by r minus 1. So we have over here the sum, sk goes from 1 to n of a times r to the k is equal to, there's your sum, which I'm about ready to drop that non-descriptive notation. Here we can factor out an a. Alright, now here, if you remember your rules of summations, we can factor out that a since we don't have an index working on that a. So this can be rewritten as a times the sum. It's really just the distributive property here. If you think about what's happening on the other side, that a is a factor of every factor of r to whatever power you're raising it to. So you're just factoring out of every factor. So this would be r to the k, and we're going to just drop this. Let's look at this side. Okay, so notice that you have a factor of a on each side of the equation, so those will divide out. Okay, now let's talk about the common ratios here, because if our common ratio in absolute value is between 0 and 1, then this term right here, as n goes to infinity, you know, if we have a number between 0 and 1 in absolute value, and the power on that number keeps getting larger and larger, then this term will tend to 0. So this sum will be r over 1 minus r if in absolute value the common ratio is between 0 and 1. If it's greater than 1, then this term's just going to keep getting larger and larger, and so you'll have to deal with that accordingly. So anyways, we've got our closed form now, so we know how to deal with sums of finite geometric sequences. Remember, this is if the domain is the natural numbers. Alright, thank you very much.